Dear students, you are welcome in the Education Department at SHAHD Association. Our lesson today is Equilibrium of Body. Make sure to subscribe to our channel for more lessons and don't forget to activate the bell to stay notified. We have four objectives for today. First, we will state the law of interaction. We will state the types of interaction. We will define equilibrium of body. And finally, we will apply Hooke's law. As we saw in the Explore section, each team is applying a force more than the other team to win. Now what happens if both forces were the same? We will see in this lecture. But first, let's state the law of interaction that's defined by Newton in his third law. For every action, there is equal and opposite reaction. That's to say, for every force, there is a reaction force that is equal in magnitude but opposite in direction. To make the principle of interaction clear, let's take the following example. Suppose that a man is pushing a wall to the right. So he is applying a muscular force on the wall. Now name the man as an object A and the wall as an object B. Now we can say that we have a force that's applied by object A on B and it's named as FA on B. So it's the force applied by the man on the wall. According to Newton's third law, there will be a reaction force which is equal in magnitude but opposite in direction. Now we can say that we have a force that's applied by the wall on the man and it's named as FB on A. It is equal to FA on B but it's opposite in direction. So the vector relation between the two forces is FA on B as a vector quantity, it's equal to minus FB on A. What are the types of interaction? We have two types of interaction. The first one, it's called interaction from a distance. It could be either attraction or repulsion. It is defined by the phenomena of the moon and the earth. The earth exerts a force on the moon and also the moon exerts a force on the earth. These two forces, they are equal in magnitude but they are opposite in direction. The second type of interaction, it's called interaction by contact. In this type, there is a point in touch between the two objects. Let's take an example. So suppose that we have a spring and an object. This object is hanged from this spring. Now we can say that we have a force that is exerted by the spring on the object, and also we have a force that is exerted by the object on the spring. Now, we will move to the equilibrium of body. If a body is under the impact of two forces, then we will say that this body is in equilibrium if these conditions apply. The two forces have the same magnitude, the two forces have the same line of action, and the two forces are in opposite direction. When these apply, we can write the condition. FA on B as a vector quantity plus FB on A as a vector also, they should be equal to 0 vector. So if we take the FB on A to the other side, we get FA on B, it's equal to minus FB on A. Let's take the following example. Suppose that this object is at rest on a table. This object is under the impact of two forces. The first one is called the weight of the object. The line of action of this force is vertical. Its direction is downward. The other force is called the normal reaction of the table. The line of action is vertical and the direction of the normal is upward. Because the object is at rest, we can apply the equilibrium condition. Summation of forces, they should be equal to 0 vector. So W vector plus N vector, they should be equal to 0 vector. So if we take the normal to the other side, we get W vector, it's equal to minus N vector. As a magnitude, we can write that W is equal to N. Now, we will move to the tension of spring. It's defined by Hooke's law. Hooke's law states that the tension and the elongation of the spring, they are directly proportional under this rule. T is equal to K times X. This force is considered to be a contact force, and its SI unit is Newton. Where T is the tension of the spring, it's measured in newtons. K is a stiffness constant measured in Newton per meter and specific for each spring. X is the elongation of the spring in meters. Let's take this example. Suppose an object is hanged from a spring. So because we have a spring, there is a tension. Let's list the characteristics of tension. The point of application is the point of contact because it's a contact force. The line of action in this case is vertical. The direction is upward and it has a magnitude of T is equal to Kx. How can we calculate the elongation of the spring? To calculate it, we need two things: the initial length, L0, or the unloaded length. Also, we need the loaded length, L, which is the final length when the mass is connected. When we have these two, we can write the equation x is equal to L minus L0. Let's do the following example. A spring has unloaded length of 4 centimeters, and when it's loaded, it has the length of 7 centimeters. The spring has a stiffness constant of 100 Newton per meter. We need to calculate the elongation and then the tension. First of all, let's write the given. The unloaded length, L0, is 4 centimeters. The loaded length, L, is 7 centimeters. To calculate the elongation, we apply this rule. So it's L minus L0. So 7 centimeters minus 4 centimeters, we get 3 centimeters. Let's convert it to SI unit. So we divide by 100, so we get 0.03 meters. Now we have the elongation. If we want to get the tension, we apply Hooke's law. So T is equal to K times X. So instead of K, we write 100, and instead of X, we write 0.03, and the calculation we get 3 newtons. Let's do another example. A body is hanged from a spring that's fixed to a ceiling. The body has a mass of 0.1 kilograms. The elongation of the spring is 1 centimeter. Using the equilibrium condition, we need to calculate the stiffness constant. From the given, we can calculate the weight, which is mass times gravity. So it's 0.1 times 10, we get 1 Newton. Now we apply the equilibrium condition. W vector plus T vector, they should be equal to 0 vector. If we take T to the other side, we get W vector is equal to minus T vector. As a magnitude, we write W is equal to T, which is equal to 1 Newton. Now we apply Hooke's law, so it's T equal K times X. So K is equal to T divided by X, which is 1 Newton divided by 0.01 meters, we get 100 Newton per meter. Now we will move to the final point, which is the characteristic curve. This table contains the recordings of different elongations and its corresponding tension. If we plot these points, we get the characteristic curve of the tension, which is a straight line passing through the origin. The slope of the straight line is the stiffness constant. We can calculate it by applying this rule. We pick any 2 points and we substitute. So T2 minus T1 divided by x2 minus x1. So 2 minus 1 divided by 0.02 minus 0.01, we get 100 Newton per meter. Thanks for watching. If you like this lesson, make sure to subscribe to our channel for more. And don't forget to click the bell to get all updates.